So it's really an honor to be speaking here. Thank you for the opportunity. So we're Taraxa, actually a public ledger specifically designed to help facilitate IoT data transactions. Okay, so I'll tell you a little bit about exactly what sort of problems we're trying to solve. So the IoT world, right? The IoT industry is actually largely plagued by the fact that there aren't sufficient number of business models, right? So when the numbers don't work out, people don't invest. So what we're seeing is that, since I started playing around with IoT devices back in 2002, until today, the vast majority of investment that's being poured into the IoT industry are still infrastructural. That means that applications, analytics, and actually the money-generating portion of these IoT applications have not really emerged en masse, right? So this is what's leading sort of to the underinvestment in IoT and actually very poor valuations of IoT companies in general. And the reason for that is, like I said before, there aren't sort of readily obvious business models for a lot of IoT data sets. And what we think is the cause for that is that there's a lack of sharing and trading of the data that's being collected by IoT devices. So there are a lot of concerns, there are a lot of barriers and obstacles that prevent IoT data from being fully traded. Whenever you see an IoT ecosystem where the data is actually open, for example, we see smartphones is actually a great example of an open IoT data ecosystem where the data is actually readily available for anyone to develop applications on. Such ecosystems become very vibrant. All participants make more money as a result, right? So, but the vast majority of ecosystems involving IoT are closed, right? So there are a lot of concerns. Why are they closed, right? So first of all, there are security concerns and privacy concerns. And I think blockchain does a great job of securing ownership and actually preventing the loss of data without explicit permission given by the owners. There's also sort of the investment concerns. So in addition to the hardware costs, you also have a lot of costs sort of involved with storage and analytics, much of which you need to sign large contracts, upfront investments with large corporations. So what we're seeing right now as an emerging trend is that blockchain technology is extremely good at fractionalizing these infrastructure resources, giving sort of smaller companies and smaller entities to actually use what they need, spend what they need, and disconnect without having to make an extremely large upfront investment, further lowering the barrier to actually sharing data. There's also a lot of concerns with becoming beholden to third parties that we actually see. I'm not sure how prevalent this is in the US, but especially in a market like in the Chinese market, where you actually work with these large internet giants who, the first year you work with them, they're very friendly. The second year, they start raising their prices and locking out your data, then they completely own you, right? So this is the danger of working with a very strong third-party platform. With blockchain, you create open, decentralized ecosystems. So you're never really beholden to any third-party entity, making sure that your business remains independent and viable, right? And of course, the last part, blockchain isn't sort of the be-all, end-all, solve all your problems kind of thing, so it cannot invent business models for you. But what blockchain is very good at is facilitating trustless collaboration between many parties, creating a very rich environment for open innovation. Any specific company or individual, their imagination is going to be highly limited. Only when you open up the data for analysis and sharing by a wider group of people all across the world, can you fully discover the potential of your data and create a myriad of business models, right? So blockchain, I think, is a great complementary technology to IoT. It can actually help to push the space forward. But there are a lot of sort of infrastructural problems involved with blockchain, and this is why we felt the need to actually create a protocol or layer solution instead of just using existing solutions. All right. So here I'm going to introduce several interesting innovations that we're introducing with Taraxa. Okay. So IoT data transactions, right? That's going to involve smart contracts. Whether you're auctioning data, whether you're trading sort of historical data, whether you're trading streaming data, all sorts of things. It involves smart contracts. And the key is, and we all know, right? Blockchain is inherently inefficient. Decentralized systems are inefficient. So if you can avoid using blockchain, don't use blockchain, right? So we want to make sure that smart contracts in sort of the business process of facilitating data trades do not become a bottleneck, right? So it's very, very fast. So if you imagine you have hundreds of millions of these devices trading data, not with, with each other, that's probably in the future, but between people or between entities, smart contracts cannot become the bottleneck. So on the same node, right, so what we're doing is on the same node, we're enabling hundreds of smart contracts to be processed at the same time via speculative concurrency, right? What that means is that, the scheduler here is just going to assume on one single node, it's going to assume that all these smart contract calls can be executed in parallel, right? Of course, that's not a valid assumption under, some cases because you're going to run into conflicts in persistent storage, okay? So what you're going to see is that we have a conflict detector that actually through the runtime libraries that give you access to the blockchain is going to track all access to persistent storage. As soon as it detects a conflict, what it does is that it goes back, stops the processes that are conflicting, rolls back the changes. So as the processes are executing, there's a log being kept to all the changes being made in persistent storage. It's going to roll them back and re-queue them for sequential execution later. So this is a very, very, very simplified implementation of software transactional memory. Okay? So this, what this does is that it helps you avoid conflicts. It helps you to not screw up when you process things in parallel. There's another layer in which we're developing a set of concurrent data structures, right? So to actually help you minimize conflicts. So if you actually imagine if you're trading IoT data and you have a smart contract that trades data, right? And that contract probably has a hash table in there with rows and rows and rows of transactions. So I trade data, that's one row. Another guy trades data, that's a different row. So by nature, those different rows of transactions occupy different persistent storage. So that's not really conflicting. What is conflicting is when you have hundreds of transactions, for example, to the same smart contract. They're all trying to extend the row by another element. They're all going to modify the index of that data structure, right? So that in itself is conflicting. But what's really interesting is that the conflicting portion is actually an extremely small amount in terms of the overall operations of the entire smart contract. So what we're going to do in creating these concurrent data structures is that we're going to make that specific operation, in this instance, writing the index, an atomic operation, which at the hardware level is just going to turn those into sequential execution. So what you have is you have a program, maybe it runs for 1 second, right? And then 0.01 second of that is actually sequential. So the vast majority of it is actually in parallel, okay? So we have a conflict detector that makes sure you don't screw up with conflicts, and we have a set of concurrent data structures which we will expose to the smart contract creators to make sure that you maximize the amount of concurrency and minimize the likelihood of conflicts and minimize the amount of sequential execution, okay? So that was interesting on a single node, okay? So what's also interesting is that how can you do this across the entire network, okay? So when you have a node that's making a smart contract call, that smart contract call actually gets routed to the smart contract creator. I guess I haven't explained exactly the topology of the underlying ledger. So the underlying ledger references the block lattice, which was pioneered by the Nano team. I don't know if they're in the audience today. But the block lattice system has a separate blockchain for every single account, and they are designed for every single smart contract, okay? So if someone calls a smart contract, the call first goes to the smart contract's creator, the guy who first deployed the smart contract. And that creator orders the smart contract calls to his smart contract into sets, right? That's very important because we all know on a DAG structure, order is always an issue, right? So that guy orders the smart contract calls. And then, so why does that person get to order it, right? So if you're a smart contract creator, if you're created a smart contract, you're the least likely person to want that smart contract to fail, right? That's the last thing you want, right? So that's some economic incentives here, right? So then what happens is that the creator orders them into sets and sequentially assigns the sets to another full node, okay? And said, you, Mr. Full Node, you're now going to process these smart contracts for me, and you get the fees paid by the caller. How does it pick which full node to choose? Well, it's aware of a set of full nodes by whatever means people advertise on forums, discovery through peer-to-peer protocols, and over time, locally, it maintains a table of reliability, right? So it says, well, this full node, the last 10 times I sent it some smart contracts, it took them forever to acknowledge me. Bad reputation, less likely to be picked. It also monitors lagging indicators in how quickly sort of the smart contract calls assign certain phone nodes to be confirmed and propagated throughout the network. So it looks at leading indicators and lagging indicators to actually figure out the reputation of the phone node, thereby modifying the likelihood of any specific phone node being selected for any task. Okay, so it assigns the phone node these tasks. That phone node does its, concurrent processing, like we talked about, and then it publishes blocks, right, containing the results, or not exactly the results, but maybe the sort of changing the network state, the hash of the changing the network state, right? But more importantly, it also publishes what's called a concurrent schedule, right? So as we talked about before, there is an order in which these smart contracts are, when they're being called, 300 smart contract calls being executed at the same time, there will be an order, right? What's also very interesting is that if different people execute these things independently, they will actually arrive at different orders because it's essentially random, okay? So it's very, very important that the order that's discovered by the initial processor actually gets published to the entire network so that subsequent phone nodes can validate it according to that order, okay? So that's how we, so this achieves concurrency on one node, so it doesn't do it sequentially. What this does is that it achieves concurrency across the network so nothing gets wasted. So you don't get into a situation where you have 10,000 miners and every single time 9,999 of the blocks are wasted, and right, only one block wins. In this one, what we guarantee is that any time a smart contract call is executed for the first time, right, where order is defined for the first time, there's only one node on the network that's doing it. So the network doesn't have to choose, right, between, do I pick you or you, right? So the concurrent stats that are being published by different nodes as initial processors will not have any overlapping contract calls. Okay. So that's the concurrent smart contract system. The second, I think, interesting innovation that we're introducing is the idea of the trustless light node, right? So I'm going to say it's semi-trustless, it's not fully trustless, right? So light nodes, so IoT devices are resource constrained. They don't have a lot of computation power. They don't have a lot of storage. Sometimes they don't even have a lot of bandwidth. So it's pretty crazy. No way can they run full nodes, right? So, but most light node implementations today, the vast majority of light node implementations today, basically latches onto a full node and say whatever you, Mr. Full Node, tells me is true, right? So that makes that light node a naive node. It basically is trusting of the full node. Now that works in certain circumstances, right? So if I own a factory and there's like 10 million sensors in that factory, and I own all 10 million of them, it's fine for all those 10 million to be connected to me in a naive way. But if, say, for example, I have a car or I have a drone, or I have some kind of a gateway in the middle of my farm that collects all the data, I want that node to be actually relatively trustless, to be more of an independent player inside the network. So the way that we can achieve that is this. So we have several designs, right? So the first one we can do is sort of vote counting design. So in block lattice, like I mentioned before, each account and each smart contract has its own chain. So being a light node, it only has to store the chains that it cares about. It stores its own accounts chain, and it stores the smart contracts it has deployed, and any other smart contract it cares to store, right? So the storage limitation is actually okay. Now the second thing it needs to store is a snapshot of the voting state distribution. So the block lattice operates on a DPoS consensus, right? So what that means is that as blocks sort of flow through the network, representatives who have votes delegated to them, as they validate these blocks, it actually comes with a vote. It comes with a signature from the representative. So others can stay on the network and count votes, right? So you count votes, you're like, this guy told me he has, he validated this block and he has 1% vote, so now I'm 1% confident, right? And that guy told me he has 5% vote, now I'm 6% confident, so you can just keep counting the votes. So we take a snapshot of the voting state distribution across the entire network, and the light node synchronizes that chain, right, the state distribution chain. So with that state distribution chain, am I running out of time? Okay. Time flies when you're having fun, huh? So with that state distribution chain, this light node is actually able to sit on the network and count votes like any other node on the network, right? So this is great. What's not great about this is that it consumes a humongous amount of bandwidth, right? Because there's a ton of packets flying around the network, and since this thing only has 3 chains, and there could be 10 billion chains on the network, the vast majority of it doesn't care about. So if that's an issue, right, you can go with sort of the bootstrapping node, in which you don't need to stay on the network, because a lot of IoT devices, not only does it have bandwidth constraints, it also goes offline a lot, right? Sometimes it goes offline for a few hours, comes back and say, what did I miss? What did I miss, right? I'm not going to sit online and sort of count the votes. What I'm going to do is that I am going to actually poll a subset of representatives and say, I care about these three chains, right? So give me a link hash of these 3 chains, and I can compare, right? Add it all up and see, oh, they all sort of add together, and they're all the same. They're all the same, so I can be confident that they're not lying to me. And I can figure out which blocks I'm missing on these chains, and I would synchronize them. Just randomly pick one and synchronize these, the sort of missing blocks. So that's how it would stay relatively semi-trustless, right? There's also data markets. Because I'm running out of time, I'm not going to go into that. I think a lot of projects are addressing this. This is a critical decentralized application. We're looking at application in terms of car data, agricultural data, as well as weather data. We have working with several partners. And this is the reason why I'm up here today. I'm hiring. So anyone who is in distributed systems, language compilers, concurrency, let me know, email me. I'll pay you well, I'll treat you well. And thanks.